Okay. I did grade the last assignment, and I graded it very easy because I didn't give you the enough material, but we covered that in class last time. So I do apologize for that. We had the Acuity Tech Talk last night, and I think this was the worst turnout class. I think we had, what did I say, something like 4 people. This is your future internship, people. So try to make time for the tech talks when they come up. They're important, and they're usually announced pretty far ahead of time, so you can try to rearrange. I know real life can sometimes get in the way, but keep in mind that some of these things are things that are going to affect you for a long time in the future. The person who presented last night, Maddie Martins, who's a alum from here, you know, she went to Tech Talks when Acuity came and visited. Now she's a full-time employee there, probably making close to 6 figures, coming back and presenting at our Tech Talks about what life is like there and that kind of stuff. So, you know, and she got her job by going to one of these Tech Talks and then following up with Jordan Lindstrom afterwards to interview with him, and then it turned into a full-time gig. She had her full-time offer before she even started her final semester in her senior year. So she came into her final semester already knowing she had a job sitting there waiting on her. And then they paid for her to come back and do a master's degree free of charge. So these are opportunities that are there with these things that's probably worth an hour and a half out of your life that you could schedule ahead, unless it's, I get it, sometimes things are just not possible, but it would be hard to believe that only 4 people were able to make it possible this entire group. So take that for what it is. All right. All right, so last time we talked about, oh, my things aren't on yet. Let's see if that's better. Well, most of them are on anyways. We'll see what happens with that guy. Okay, so last time we talked about arrays, and we really talked about this idea of requesting memory. And once we officially request memory, that memory is now ours that we can use for as long as we want to use it. And then we should give that memory back when we're done as a good steward. That's what that delete thing was. Now, like on exams and stuff, I won't take off points if you don't delete memory that you created. So really, I want this to be something you kind of just remember in your head, that if you make a mess, it's your job to clean up that mess. And then sort of kind of appreciate that even with an older language like C++, the modern runtimes for these guys clean up your mess for you. And when you get into a language like Java, which we'll look at next semester, that language doesn't even give you a way of cleaning up your mess. It cleans it up for you using automatic garbage collection. It's a feature of the language, the idea of automatic garbage collection. Okay. That being said, let's start talking about objects. All right, so if you remember back to probably the first week of class, something like that, we talked about, might have been the second week, we talked about object-oriented languages versus procedural languages. I used the example of like the object-oriented telephone versus the procedural telephone. Mentioned the procedural telephone's the big pile of wires. The object-oriented telephone looks like a telephone. But we know that inside that box that is a telephone, there is details, there is stuff inside there that we do have access to. like the keypad and the headset and all that stuff. But we also know there's a bunch of details in there that we don't have public access to. And that telephone has become easier to use because the details that we don't need access to are packaged inside. And then we can just hand the phone around to folks and they can just use the public interfaces of that phone to solve problems that involve phone stuff. Okay. So, object-oriented programming. And this pretty much goes across the board in all languages. Involves a keyword called class. A class is a collection of fields, constructors, and methods. I'm going to put in parentheses here, functions. So methods are the same thing as functions. They're synonyms, let's say. All right, but let's kind of define each of these guys. A field is a variable owned by the class. A constructor is like a function, and it must match the class name. I'm going to say its name must match the class name, and we'll see this as an example today. But it does not have a return type. All right. So up to this point, all the functions we've written, the syntax for a function is return type, function name, parameters, and then the body of it does stuff. But our functions always have a return type, even if that return type is void. All right. Constructors, these guys will never have return types, but they still look a whole lot like functions. Their name is always the same name as the class, and that'll make more sense once we dive into it here in a few minutes. It still takes a set of parameters, and it still has a body where you accomplish stuff. The job of the constructor is to initialize the starting state for a newly created object. I'll just say an instance of an object. It's kind of a, you know, when we might have a class and we use that class as the blueprint for building 5 instances of the class. So today we'll probably write like a person class. Okay, so you can create a person class that's an instance of that person and that person and that person. We use the exact same blueprint, but that person had a different first name and last name than this person, and a different first name and last name than this person, so on and so forth. Okay. So a constructor does that initial constructing of a object. Then a method is a reusable chunk of code. Actually, let's, I'm going to make it a little bit more class specific in this. Represents the abilities of a class. Some of these abilities are publicly available. Others are private and only usable within the class. Okay, and that kind of goes back to that idea of the object-oriented telephone, where we know when I hold up my phone, we know there's a bunch of complicated stuff in here, but I have a power button over here, so that's a public thing. I have a volume button over here, that's a public thing. There are aspects of this phone that have been made available to me so that when I'm passing this phone around, it doesn't matter who has it, they have the ability to hit those public elements. But we also know there's a whole bunch more detail inside of this thing that is not publicly available, but is still important for the inner workings of this phone. Make some sense? All right, so these methods, they represent the abilities of our object, both public and private. Okay. Now I'm going to reference kind of an older thing. We have something called a struct in our older languages. So a struct is a collection of name value pairs. So at this point, we've looked at single variables where a variable can hold a single value. We've looked at arrays where an array can have a single variable name and hold a whole bunch of values. The idea of a struct is we have a single variable that knows how to hold several values, but those values don't need to all be the same type and they're labeled. So we can have a struct that says, here's the first name of a person. Here's the last name of a person. But what a struct can't do is it can't house functions directly. There's kind of a hack that allows you to kind of pull it off, but that's kind of where object-oriented languages were born out of. All right, so we can say that a struct is effectively a class that does not have constructors or methods and lacks the concept of public/private see what else do I want to say about it. I'll put a little caveat in here. I'll just say, put it a note. And this is an important aspect of structs related to what we talked about last class. We're actually not going to do much with structs in here. We're going to jump right to objects, but I at least want to get this stuff academically out here. How many of you, not that I expect the answer to be yes from most of you, but how many of you have worked with Python before? Okay, a couple of you. So, and you've worked in Python, there's a popular data type called a dictionary. Okay, so a dictionary is a collection of name value pairs. It's effectively like a struct, but what I'm about to say next is a differentiating factor between dictionaries and structs. So structs by default are passed by value. Now remind me, what's the difference between passing something by value and passing something by address? Go ahead. Okay, so when I pass something by value, I'm handing that function, presumably I'm passing something to a function by value. I'm handing that function a copy of that something. So any changes that get made inside that function die when that function ends. There's no side effect. When I pass something to a function by value, I'm handing it the address where you can find the original. And when you make changes to that place in memory, there is side effect. You're changing the original one, not a copy. Okay, so pass by value versus pass by address. One is not necessarily better or worse than the other one. We can just imagine that they are good for solving different problems, right? Now, structs, if you create a struct and you just pass that struct to a function, its default behavior is passing it by value. Changes you make to that struct inside of the function will not be noticed outside of the function. When the function dies, those changes get erased. Just like if we passed an int to a function. Now, we can pass a struct by address using the little ampersand thing, right? You know, I did a dollar sign, right? That's the ninja move, right? So we can say, here is the address of a struct, and we can have a function expecting a struct pointer, in which case now I move beyond the default behavior of a struct, and I'm saying, hey, I'm explicitly giving you the memory address of this thing. You're explicitly expecting a memory address with the intention that you're going to make some changes to that struct internally, and those changes will be noticed externally. Okay, but that's a choice that we're making as a programmer. The default behavior of a struct is to be passed by value. Now, the reason I made that differentiation here, and I'm going to make it again when we talk about classes, is in Python, this dictionary data type, which is a collection of name value pairs. Basically, it is a struct. But because of the way it's implemented, the default behavior of a dictionary, when I pass a dictionary to a function, it is passed by address in Python. So it has a different default behavior in Python than a struct does in C and C++. That isn't necessarily a problem. That is just kind of, you know, I kind of mentioned the first week of class that programming is the skill set. The language does not matter, right? And that's largely true, but each language does have some nuances to it. So sometimes when you're working with a language you haven't worked with in a while, let's say, you might have to say, oh, I wonder how this type behaves in this language. And you just run a little experiment real quick. You create a function that takes in a struct, or write a function that takes in a dictionary. You try to make a change to it, and you see, did that change get noticed outside? If it did, the default behavior is it's passed by address. If it didn't, the default behavior is it's passed by value. So sometimes you might run a couple little experiments on the types you're about to deal with just to make sure you understand the tool that you're about to use to solve the problem. Make sense? Okay, and that's not necessarily dissimilar to how things work in real life. You know, if you, not all screwdrivers are created equal. Some of those screwdrivers, you know, that you have that standard screwdriver that you turn and it doesn't have the ratcheting thing inside of it, right? But other ones, you know, you turn left, it doesn't turn. You gotta hit the little switch to make it do the tighty thing going one direction versus loosening thing. So even though they're both screwdrivers, the tool is slightly different, and you might need to familiarize yourself with it for a couple of minutes before you just start solving all the world's problems with it. Make sense? So this isn't dissimilar to real life, but it's something you do want to keep in mind, that as you do go from language to language to language, there are some nuances like that where you have to say, well, how do I accomplish this thing in this language? And is there anything kind of special behavior we need to pay attention to? Make some sense? All right, so we're not going to actually mess with structs in here too much because they really aren't a common player in today's world. I'll just show you a quick demonstration of it so we can use it as our example, but I'm not going to test you over this. I won't have you use structs on exams or anything like that. Let's see. I want to create a new. Well, actually, yeah. Let's just do this. Let's save. More projects, new project. Let's save this one. CSC200 class intro. All right, so just to kind of demo this real quick, I can create a struct data type. So let's call this guy a person. And I can say that a struct has a string first name and a string last name. And then out here, I can say struct person P1, struct person P2, P1 dot F name is equal to Mike, P1 dot L name is equal to Whitman, P2 dot F name is equal to Dave, P2 dot L name is equal to Smith. Okay, good. So I'm trying to use cout to print out this new struct. Now, cout is a function that was already built into the language, right? Did it know about the thing that I just invented 2 minutes ago? This dude, it doesn't know about that. I can say, print out that dude's F name, because cout does know how to print out strings, right? We've seen it do that. Here's my struct. What is F name? F name is a string. L name, also a string. But if I say print out P2's F name, that guy's name is Dave. So I've invented my own data type here called a person. I created 2 variables of type person. And then I filled those variables up with the name value pairs that it expected. Expected a first name and a last name for both of them. All right, that makes sense. Now, if I were to write a function, change struct, this guy took in a struct person P as a parameter. Let me also just say void print person. So this function called print person, I pass a person into, and he just prints out the first name followed by a space followed by the last name. Mike Littman, Dave Smith. All right, that's what that function does. Change struct here. This guy's just going to say p.f name equals Bill. He's going to try to change that guy. Then I'll call out print person, passing it P here. I do need to prototype these guys up top. That my code knows about them. All right. So I created my couple of people there. I'll just go ahead and call print person P1, print person P2, just to test to make sure it knows how to print out those person objects. So there's my function, print person, that takes a person in as a parameter and spits out that person's full name. All right, but now what I'm going to do is I'm going to call change struct. I'll pass it P1, but then I'll print out that person again. So change struct takes in a person, changes his first name to Bill, prints out that person, proving that the name has been changed. But then when this function ends and we return control back to main, and I go to print out the person, P1 should revert to its original. So it was passed in to change struct. I was able to change it inside of change struct. But when change struct ended, I see that that struct was passed by value because I'm back to my original version of P1's first name, which is Mike, not the Bill that I changed it to inside. It was operating off a copy. That makes sense? Now, if I wanted, so that's the default behavior of a struct. Okay, I can have it take in a struct pointer. Oh, let's do it on this one. And then I can change star P's first name to Bill. And I can print out star P. And then when I call change struct, I can pass it the address of that struct. Ooh. Oh, he's already stored as an address. Oh, interesting. So it actually says I can just use it directly. Reference. Taking in a struct person pointer. That is the value of that guy. Oh, you have to use that syntax for, I'm going to be showing you this for classes anyways. It doesn't like that either. Change struct. Oh, it's because I redefined my prototype. It now takes in a pointer. Yeah. So now I do need to pass it my correct thing. He wants an address. All right, and we see that the change was permanent when it came back out. So having said that, I could have done this. Let's make sure I can do it. I think I can do it like that. And I need to put it in parentheses. And I'll cover that more, but that right there is the same as saying P with an arrow F name. But I'll talk about that in a lot more details when we talk about classes, because it's kind of the same thing. But in any case, with structs, I can hold name value pairs, and that's it. That's all they can hold is name value pairs. They can't hold functions. They don't have constructors to help you build one. So notice I created this struct right here. I had to manually fill up its values. There's another one I had to manually fill up its values. There are some ways of getting it to be more user-friendly, but in general, I think this is the truth. Okay, they're not as convenient to use as objects, but they accomplish a task. They allow you to have a single variable associated with several name value pairs. And we saw that by default, they are passed by value. All right. So we're going to say that let's pretend we're a C++ programmer back in the, I don't know, early 80s or something like that. Object orientedness came out before that. But let's say that we're a C++ programmer in the early 80s and the programs that we're writing keep getting more and more complex because the types of problems that we're using computers to solve are becoming more prevalent. So now our programming languages, which were maybe delivering for us yesterday, start showing some weaknesses. We aren't quite, remember when we first talked about programming languages, we said one of its jobs is to allow us to solve problems in real life that's very similar to how, or solve problems in the computer that's similar to how we solve problems already in real life. Try to meet the human being 99% on our side. Only having that 1% be, how do I speak computer, right? All right, so with that in mind, now we start saying, you know what, I kind of want to build a telephone and be able to hand around that whole telephone with all of its functions between my parts of my program. And I can't accomplish that in my original C code. Okay, because the C programming language did not support objects. That's why we're using C++ in here. Okay, the C programming language was a procedural programming language. It had structs, which maybe allowed you to pull off things a good number of times, but it did not allow you to conveniently create things. Now, I could build a constructor here, so I can say struct person, make person. And this guy could take in a string F name and a string L name like this. So this guy is going to behave kind of like my constructor for a person object, person struct. Oh, I also need to pass it the struct. Actually, I don't need to. I'll build it inside here. This guy will create a struct person P, and it'll say P.F name is equal to the F name that was passed in, P.L name is equal to the L name that was passed in, and then return P. So this function takes in two strings, a first name and a last name. It builds a struct, it sets that struct's first name and last name, and then it returns it. Good. No, because I'm returning it. Yep. So you're right. If I had passed in a pointer to it, or not a pointer to it, the original one. So inside of this function, I am building a brand new struct. I'm filling it up with my values that I passed in, and then I am actually giving it back to whoever called it. I'm not relying on them finding it in memory somewhere. I'm handing it back to them. So now what I can do up here is I can say struct person F1 is make person Mike Whitman. P2 is make person Dave Smith. So now I have a single function that I can throw my couple of strings at. He'll build me, he'll construct me a struct and then hand it back to me so I can now do things with it. So same output. Same logic as we had before, but we might say, hey, this looks a little bit better, right? I'm now relying on this generic function here to take in my first name and last name and go ahead and build me a struct and give it back to me. That guy is effectively a constructor for a struct type person, or a person struct. All right. But the problem here is it's not self-contained. We're still looking at the pile of wires. All I've done here is I've just kind of have a centralized section of that pile of wires over here that I can toss a couple of things at, and then I can kind of pick up this other wire. That's the answer. It's still all out in the open, right? Does that make some sense? So you can pull this off if you put yourself into the shoes of an old style C programmer, and the problems you're solving keep getting more and more complex. You can imagine that, yeah, for our example right here, this isn't the end of the world. You know, we're not running looking for alternative programming languages just because of this. But as the problems get bigger and bigger and bigger, this does become more of a problem. So we might say, well, is there a fix? Right? And that's where classes come in. So I'm going to create a class. I'm going to call this guy a person class because I already have a type called person. Okay. So just let me get away with that for our example here. All right. So here's my person class. Start off with that. Now, I'm not sure if it requires me to put in a private and public section, so let me just try it without it for a minute, because I want it to look as close to my struct as possible. I'm going to steal this. Here's my constructor for my person class. It must match the name of the class. Notice it does not have a return type. And then I'm going to go ahead and steal. I'll just rewrite it. So now I'm going to go ahead and I'm going to write another function called display that takes in nothing. And he's going to see out. We'll talk about this keyword here in a second. Let's just get it out there first. So now my person class, I mentioned in the slides here that a class is a collection of fields, constructors, and methods. So back here, rather than having the struct manage my fields, another external function managing my construction, and another external function managing my ability, a method for it, I can now bring all those things under a single hood. I have a class that's holding on to some fields, a constructor, and in this case, just one ability, one method. So now I can say person pointer P3, a person class pointer P3 is equal to a new person class P3 display. Oh, I still have my return statement in my constructor here. That's what we did before. Okay, it does make me do the public and private. All right, so I'm going to say that's my private section. And this is my public section. And we'll talk about what that means as well. So basically a person class can hold on to its first name and last name privately. And we'll see why that, I could put them publicly. It wouldn't hurt anything. In fact, actually, let's do that at first. I'll just dump the private section. And then let me get rid of this guy, and this guy. P3 display, here's my P3. This is what display does. Oh. I'm still building my constructor wrong. I just copied it in there. It didn't change anything. So there's my class. So my person class has two variables here. I'll put a little comment before these are the fields. These are the constructors. In this case, I have one. You can have more than one constructor. And I'll show that to you in a minute. And then these are the methods. So it's all self-contained inside of this single pod called the class. All right. So now I can come in here and I can say, I'm going to create an instance of my person class. This is an instance of person class. And as I'm building it, I'm going to call upon the constructor, passing it the two strings. This is the constructor. Notice it matches the name of the class. Those two things came in. It's expecting a string F name and a string L name. Then I'm using this keyword. I'll talk about that in a second, but I'm using this guy to set this particular instance's first name field equal to the first name that you passed in. I'm then setting this particular instance's last name field into, I'm passing it the value L name that was just passed in. These do not have to match, but they probably should. Because the reason I named it F name up here is because it's holding the first name. And if I'm expecting the person to pass in a first name here, why wouldn't I name an F name again? If that's how I want to represent the idea of a first name inside of a variable called F name, a lot of programmers who don't understand this keyword will say, oh, well, I'll just change the name of this guy so that I can say maybe something like that, F name equals FN. So it can tell the difference between, remember, all variables resolve to their most local definition. So now it could tell the difference between F name resolving not to anything here, but to the guy up here, and FN resolving to this guy here. By having them be different variable names, I can bypass an understanding of the this keyword. And the this keyword is integral to understanding how classes work. So basically, you name your variables in a meaningful way. And if it was called F name up here, it probably is going to be called F name here. So how do I differentiate? I make sure I'm talking about the field owned by this particular person class that I'm in the middle of building right now. And I'll kind of prove that to you here in a second, what I mean by that. All right, so this is a constructor. His job is to initialize an instance of a class when we first create it. So it's taking in a first name and last name. It's setting this guy's fields equal to those values. Now, I could do more stuff in there, but in this particular case, that's what it means to instantiate a person class. Set his first name and last name. Class is kind of boring. But notice it does not have a return type. And the reason it doesn't have a return type is because his whole job is to create this dude right here, this keyword. He's to give him a value, okay? Which means that a constructor always produces a memory address. Therefore, why should we have, well, first of all, we don't, I guess the type would probably be void pointer that would come out of there, but why should we have to mention what its return type will be if the return type is always a memory address? Make sense? So the way we let C++ know that this is a constructor is by naming it the same thing as the class name. Now we treat it as a constructor. The compiler's cool with you not having a return type because constructors return memory addresses. and life goes on. Now we get to our methods. These are plain Jane methods like we've dealt with before. It has a return type, it has a name, it also has a set of parameters, but I'm not passing any parameters here. Who do I want it to display? I want it to display the first name and the last name. But because this method is defined inside of this class, it's part of this pod, okay? He already knows about the first name and the last name of this particular person class, okay? Just like inside of our cell phone, there's this guy has a a card that talks to the a SIM card that talks to the towers, right? And that SIM card knows what my phone number is. Okay, so if I want to, well, maybe even a better example would be, let's say I want to call my mom. This guy already has stored inside of it the information that is my mom's phone number. So I don't have to say call and then hand it that number. I can just say call mom, and it goes and looks up locally inside of here what the phone number is and makes the call. This instance of a smartphone already knows about my mom's cell phone number. Okay, now you have a cell phone, don't you? And you don't have my mom's number in it. I hope not. And then, you know, so you have a separate instance. Maybe it's a different model phone, but we'll just generically call these guys smartphones right now, right? So his instance of smartphone is the same thing as my instance of smartphone, except my instance has stuff inside related to me. Your instance has stuff in it related to you. Okay, even though it's the same kind of stuff. I presume you have a bunch of phone numbers stored in there of different people, right? Okay, so that's why this display method here doesn't need any parameters, because his job in this case is to display what this person class looks like, or what we imagine a person class might look like. And I don't need to give him any inputs to work because he already knows about the first name and last name of this particular person. All right, make some sense? So that's why down here, I create my person class instance, P3, and he's equal to a new person class. I can then create another person class, P4, and he's a new person class. And then I can tell P3 to display themselves, and I can tell P4 to display themselves. I'll go ahead and get rid of the struct stuff here. Actually, let's just comment it out so you'll have it for your. So now I'm using the single blueprint person class with this constructor, and I'm creating two separate instances of a person class. So this first guy is an instance of person class. The second guy is also an instance of person class. Just like this is an instance of smartphone, and that is an instance of smartphone. Two separate smartphones with similar but different information inside them. Make sense? So now if I want this guy to display itself, I ask P3 to call his display method. Okay. You might ask your phone to call your emergency contact. I might ask my phone to call my emergency contact, which is Mr. Gonzalez, by the way. Lots of silence when they call him. So both of our phones have a method in them called call emergency contact. What is it? ICE is usually you put it in your phone as ICE. But when you call yours, it calls a different person than mine would call. All right, because your instance knows about your stuff, my instance knows about my stuff, but they're both smartphones. Both of these guys are person classes. And they both know about their own stuff. So I don't need to pass anything to display because P3's copy of the display method knows about the stuff that P3 has. That was set when P3 called his constructor. Make some sense? So there's my Mike Littman and Dave Smith object-oriented style. Go ahead. What? No. We'll take a shot at it. We'll see what we figure it out.
When you call it person class there, it's actually so P3 is that like a new?
This is a variable. Yes, that's a variable name, and he's of what type? Well, so let's break it down. So P3 is the name of a variable.
Right.
We're good with that? Now, whenever we define a variable, I'll just create another line right before this. So if I say int a is equal to 5, a is a variable, its type is int, right? This guy's type is person class pointer. Now, what does a pointer hold? We'll break it down. An address. Okay. So specifically, this variable here is built for holding the address of one of those guys. A person class, which I invented up here. Somehow, for our perspective right now, somehow all that information. All right. But all we need to think about for this left-hand side of the equal sign here is that this is the name of a variable and he's capable of holding a memory address. Specifically, it'll be a memory address that goes to a place in memory where a person class lives, whatever that guy is. That's what this variable knows how to hold, just like this variable knew how to hold an int. All right, so we're good on the left side. Okay, that's just what it is at this point. Okay, we don't have to know what a person class is at this point. Just that's what it is. So now we go to the right-hand side of it. What's the new keyword? What's that guy's job? Yeah, so that's our real estate agent we talked about last time. So this guy goes and finds a memory address for us. Okay, which is good because this guy's built for holding a memory address. Okay, so this guy's going to go and find a memory address for us. Now, how big is that memory address? Let me give us another example here. So I'm going to say int. Actually, let's do it this way. So in this example, another variable that we talked about last class, my variable name is AR. This guy's capable of holding a memory address. Specifically, it's the memory address to an integer, which is the base, the first integer in a collection of integers. Okay, but AR holds a memory address. That's what this guy says. And that memory address is labeled as a memory address that points to an int. Then I'm calling my new keyword there again. I'm saying, hey, go get me some memory. And he's going to run out and talk to the operating system and get enough memory to hold this many of these guys and then spit that answer back out. And that's going to get stored in AR. Okay. Something very similar is happening here. The new keyword is going to say, you want new memory from me? No problem. I'm going to run out and I'm going to ask the operating system for enough memory to build one of these guys. This part here, this is me calling our person class constructor, kind of the thing that's like a function. So my person class constructor thing here, he takes 2 strings as parameters for him to do his job. The answer is yes, 2 strings, and then let's call it a little bit more. There's some overhead to build the structure in memory, but largely what you said is accurate. That there's going to be a place in memory that needs to hold 2 strings, and, but really what's a string? A string is actually a pointer to some other address somewhere else. But yeah, I mean, I think conceptually that's correct. That's as far as what we've designed right now, a person class holds these pieces of information, and then all this logic operates on those pieces of information. So I think it's pretty fair to say that the size of a person class is roughly the size of 2 strings in this place, in this situation. So that means we're asking the new keyword to effectively say, get us enough memory to hold 2 strings. The generic way of saying it here would be, go and get me enough memory to hold an instance of person class, whatever that is. We've talked about the size. So for instance, here, we've talked that we know an int is 4 bytes big. We're asking for 10 of those. So I'm asking the new keyword to go find me 40 bytes. Find me 40 bytes of memory in memory. For computer scientists, we're learning what's under the hood and stuff like that. This is all fine and good, and we're in school. This is academics, and it is important stuff. But at the end of the day, do we actually care when we're writing our code how much memory this dude found for us, as long as it was enough? Go get me memory that's enough for what I want to do. So the way you're thinking about it is good, that this guy is 2 strings. We're going to. Yeah, it is very difficult to talk about this without saying this, but it's a good one. You should still be confused about the this keyword, as well as the arrow thingy. Okay, those 2 things. Go ahead. Yeah, I've abandoned. I commented it out. So it's an ability, but I'm not using it. I'm just going to keep it in here. So when I give you the code, you kind of have the 1968 version of what could C pull off. It's similar-ish to holding the person, to the modern day version of how do I hold a person all in one pod instead of having, his abilities spread out all through my program. Go ahead. Walking back through why we're using functions. Okay. So why are we holding this in a pointer? Yes. Okay, so that goes back to this. So if we roll back to the beginning of class today, I mentioned that, or early in class today, I mentioned that structs by default are passed by value. Classes are passed by address. And this is really the answer why. Constructors are very much like methods, very much like functions. We can use those terms interchangeably, with one exception. They do not have a return type. And it's because the return type of a constructor is always a memory address. So that means whenever I'm calling upon a constructor, I'm going to be getting a memory address. And that means if I want to hold the place where that object was created, I need to hold the memory address. I need a variable capable of holding a memory address, because that's what I'm going to get. That's just how constructors work. So the way object orientedness was handed to C++, and this is true across the board in all object oriented languages. In Java, this is true. You don't have a specific syntax for pointers in Java, but in Java, if I were to go and do this, I'll just print out P3. And P3, we know, is a person class pointer. We expect to see a memory address here, because that's what P3 knows how to hold. There's our crazy memory address. Now, that's not that meaningful to me, other than the fact that I know that this guy is on this street somewhere down this big, long street. Go ahead. Because the value of P3 is an address. That's P3 is a variable, right? If I said this, now it's going to try to show me the value at that address. And we're probably going to get it, it's probably going to yell at us, because it's going to say, hey, C out was written a long time ago, way before this dude that we just invented. So it's going to say, look, this operator, basically C out, doesn't know how to work with person classes. You just told me to print out an actual person class, not the address where one lives. But remember, the star here says, give me the value at this address, which is a person class that cout doesn't know what you mean by displaying. That's why we wrote our own display method, which can do our version of what we think displaying a person class should mean. In this case, putting out the first name and the last name. Go ahead.
So in the person class, do you always have to use the this keyword when you're trying to see the keyword?
For right now, let's say yes, until I talk about how this works with the this keyword. See, it's already started. You can't talk about this without saying this. All right. Yeah, so in any case here, when I print out P3, I'm going to get a memory address. If I print out P4, I'm going to get a memory address. All right, go ahead. Sure.
Okay, so in the fields part, we define two variables that we're going to be.
Yep.
Then we move down to person class, and when we call that later, we construct it. This is the first name we pass in this last instance, and we attribute it to this instance of those variables.
Yep.
Then our method just displays that instance.
If it were called.
Okay.
Yep, this is an ability of this class. Yep.
And the constructor is a function that by necessity returns
A memory address. Yep. All right, so now let's start talking about the this keyword a little bit. But first, I'm going to prove something to you. So let's first define it in words. The this keyword. The this keyword is how an object refers to itself from within itself. So obviously that cleared everything up. All right. Well, first let's look at our real life example of this. When I say me, what am I talking about? Myself. When Aiden here says me, who's he talking about? Okay. I'm going to replace the word me in our vocabulary now. This. When I say this, I'm talking about things related to me. This is first name is Mike. This is last name is Littman. This is first name is Aiden. Okay. So this relates to an object as me relates to us. It's how an object in a human being, or building person objects, they're not as complex as a real life person, but they're a start. Okay. This keyword is how an object refers to itself from within itself. Okay, that makes sense? And I'm going to show you why we need that. All right, but at least conceptually, we've moved a little bit forward. That this keyword is kind of like us saying me or I. Some languages like Python use the keyword self. Myself, so self and this and me, these are all kind of the same. They're accomplishing the same things. It's how an instance of an object talks about itself from within himself, inside of his functions and stuff. So we just saw here, when I created P3 and P4, and I printed them out, I got a memory address, right? Because P3 is built to hold a memory address. And that is the place in memory where P3, where the instance that we've associated with P3 actually lives. What I'm going to do up here in the constructor is I'm going to say cout this. Let me take my displays out just so we can, when I built P3, I built P4, As part of the building process inside the constructor, I went ahead and printed out the value of this. Okay, whatever that was. So inside of that instance, as he was being born, as that instance was being created, I went ahead and printed to the screen the value of this. Outside here, after he had already been created, I printed out the value of P3 and the value of P4. And what we see here is when I was building P3, that was the value of this. When I was building P4, that was the value of this. They're similar values, but notice they are a little different. This guy's EE0, this guy's 340, at least the last part of it. After he was already built inside of main, see, these two values were printed out inside of those constructors, inside of the instance of the class. These two values were printed out inside of main. This is where I printed out P3 in main. Notice that it's the identical address as the value of this inside of the constructor when I was building P3. This is how an object refers to himself within himself. And why do we need that? Let me go to my constructor here. It's because I can't say that. If I'm inside this constructor, even though I'm in the middle of building a variable out here called P3, the scope of P3 is local to main. I don't have access to that variable inside of my person class. So if a person needs to be able to, so out here, P3 is how we're able to talk about this instance. Okay, that's our pointer to that place in memory. But inside of my constructor, this points to that same place in memory. It's the variable that all objects come with. This is the secret sauce. This keyword is the thing that makes object-orientedness work. Because objects come with this variable that allows a class, allows an instance of a class inside of himself to talk about the same place in memory that where he lives. That variables like P3 and P4 outside of that class are able to talk about. I can ask P3 to display himself. So that's saying, hey, you up there at that memory location. Doesn't matter how I got to that memory location, whether it was from P3 or whether it was from this. I want you to call your display method. So I can say it right here. I can also do that inside the constructor. I can set the values and then I can yell up, hey, you, same memory location, call your display method. So this and P3 are equal to the same value when P3 is being built. This and P4 are equal to the same value when P4 is being built. So there's our, I think I printed out P3 out here, and then there's my P4 and P3. Go ahead.
So even really with that basically, we created something without
Yep. Good point. Yep. So up to this point, we've been always prototyping things beforehand. So with a class, it kind of is a package deal. Everything inside this class is in scope for that class. We'll talk a little bit more about the difference between the public and private stuff as we get into it. But as of right now, everything is in scope. All right, let me quickly get a homework assignment out and then I'll It's going to be impossible, but I'm going to make it easy. It's going to be literally copy from this, but instead of building a person class, we're going to build a car. Car may have a name. It might have a number of wheels instead of a first name and a last name. Okay, just enough to get us used to the syntax. So homework. Create a car class that has a number of wheels and a name. Number of wheels, I'll say might be an int, and a name is a string. Create a constructor. Create a display method that, when called, displays the car in some reasonable way. Example. Well, that's not the right. Corvette with 4 wheels, something like that. Submit a link to the code and the self-assessment. And what I'll do as a starting point here, I will save this. I will give you the code to this. And I'm also going to go ahead and paste it into Slack just in case there's any issues with that sharing it thing. Okay, so any questions what I'm asking you to do? Just duplicate what I've done here, but instead of building a person class, we're building a car. And instead of it having a first name and a last name, it's going to have a name and a number of wheels. Okay, I want you to get used to using those things. It should still be a little fuzzy for you, but we're going to keep connecting those dots. Go ahead.
Okay, so 2 things. One, we're not missing with like the struct, the change struct.
No, structs are not part of your life from this point forward until I refer to it in another class.
Okay.
Structs were our baseline for today that said this is why we need classes. You won't be tested on structs. I won't ask you to read code that has structs in it. They were the old way, and classes are better for us right now. Okay? What was the second thing?
When you're using this, the reason it's returning a memory of address is the star, right? Like if I said
Object, no, it's because objects are always created in memory. So by default, they're passed by address. So that this keyword holds a memory address.
yeah, but like it wouldn't always return like 0x55, right? Or like,
It'll always return some, if you printed out this, it'll always be some memory address.
okay.
It might not be the same memory address, but it'll be some memory address.
So it couldn't be like
No, it would not be.
okay.
It's always an address. It might be the address where Mike Littman lives, where those values are stored, but it will always give you an address because that's what this holds.
Okay, thank you.
Yep. Sure.
Classes are then passed by address.
By default, and out of a necessity, because that's what the new keyword does.
Perfect.
Yep.
And then, could you have in your constructor instead of just saying see out this, if you were to call asterisk this, would it print it out the instance? So instead of the memory address.
Well, no, because then we would have gotten the same error we got earlier, because star this is an actual person class, and see out doesn't know about person classes.
Gotcha.
So that function, that old function that see out was written years and years and years ago, it doesn't know about the dude we just invented. So he doesn't know how to display a person class,
Okay.
because star this is a person class, not a pointer to a person class. It's the class itself.
Gotcha. So like see out, let's just say this reference See how it was built last year, person class was built this year. They both are like functions of things that can do things, but this one doesn't recognize and do it.
Well, C out only knows how to display certain things. It knows how to display all of our primitive types, and it knows how to display memory addresses. That's
So it
that's
can't
what it knows
dis-
how to do.
It can't display the display that we've just created.
Well, when you say star this, you're not saying call display. You're saying here is an actual person class. It's like me lifting you up and saying, see out, show me this guy, and expecting it to figure out what it means to show a person class.
So it just can't recognize that because that our person class wasn't around when CL was built.
Correct.
Okay.
So yeah, it wasn't taught, and that's a good thing, because that if it was, that means that we would not be able to keep inventing types like this.
Gotcha.
In Java, we have a special function called toString that we can write inside of a class that teaches Java's equivalent of cout to display something. Because what cout does, it says, I know how to print out any primitive type. I know how to print out memory addresses. And as a last resort, if you give me an object, I'll try to call his toString method. So if you update that toString method to something that makes it show up, it'll actually show up as the contents of the person, but only if the programmer does that. The default behavior that comes from object in Java is a memory address.
And last thing, this is kind of like an analogy type.
Okay.
So for our homework, it's kind of similar, like a class would be like an assembly plant. We're passing in, I want a red Corvette that has this many wheels and this many seats. And then we're gonna call upon this assembly plant. They're gonna say, here is this car.
Yep.
Oh, okay. So it's kind of like you pass in, or it's kind of like a giant function almost.
Well, I mean, I like the assembly kind. I like the factory idea there, where we've created the blueprint once, and that blueprint knows how to build Corvettes with a color.
Yeah.
And I could say, okay, I want a Corvette that's in red. I want a Corvette that's in blue. They use the same blueprint,
Gotcha.
but the dude who's making the car for you brings in a different can of paint, depending on whether he's making a red one or a blue one, depending on what you asked for, even though he's using the same blueprint for building it.
Gotcha. So like the same analogy could be used. This is a clothing factory. I want a sweater that's made from cotton and a sweater that's made from wool.
Yep.
Okay. Got it. All right. This is fun.
Well, it should be. It should be a little fuzzy still, but it's good. You're asking the right questions.
I like this. This is challenging.